So this is currently the mode of operation in Flink. So pipeline execution. The system is moving to a more hybrid approach. So very soon there will be the engine will support both blocking, so batch or stage execution, and pipelining. And the plan is to basically use pipelining for streaming. For batch jobs, use a combination of pipelining and blocking. So in many cases, you would like to create a stage, pipeline within that stage, and then create a second stage, and so on and so forth. And for interactive programs, programs that bring back results to the client and then go back to the cluster, you want at some point to block. So the system is moving towards this hybrid approach. The second point was memory management. So all I tell you here is the following. So Flink, when it starts, it's going to allocate memory in the form of byte arrays, memory segments, and everything is going to happen inside this managed memory. So the heap is divided to a managed part. This belongs to Flink, and it is all the memory for sorting, for hashing, for intermediate results, for network buffers, and so on. And an unmanaged space where the objects of the user code live. Yeah. Now, every component of Flink internally is written to is implemented to work on these kind of memory segments, to allocate these memory segments, to deallocate these memory segments, move them to disk, bring them up to memory, and so on and so forth. So in the end, what you get is hardware and this on memory. This has actually some very nice user-facing consequences. The first one is that the system requires very, very little configuration. So in order to run Flink in very data-intensive jobs, you need to configure the following. So the first is the parallelism per job. And then for the system, the total heap size you're going to give, and the percentage of that heap size that will go to the system, and the percentage that will go to the user code. Yeah? There's a third parameter, which is the size of memory for network buffers, but we'll very soon getting rid of that. So with only these configuration parameters, we have run actually Flink in extremely data-intensive jobs, and the system will not throw an out of memory on you. Another benefit of managing your own memory is that you can get much smoother performance. So the way that the algorithms can spill the disk is not via relying on the operating system for paging, but by trying to optimize the I/O. The garbage collector will not hit in so badly, so the performance curve you're going to get is much more smooth in most cases. Yeah. Any questions so far?
Are you using off heap?
Not currently. There is a pull request that will be merged soon that is enabling that. So in fact, all of this right now is living in the heap. Yeah. The only thing we need to change to go off heap is an implementation of the memory segment class that lives off heap. So yes, actually very soon you will be able to move that stuff off heap.
I can add to this in the sense that all the algorithms internally are written more or less in almost in a C++ style fashion, so they're not using objects, they're basically using pointers, if you wish. I mean, pointers in Java go down to, let's say, offsets and byte arrays. But there's very little change to actually turn this into a proper pointer that points to some memory out of the heap. So that's why we can actually do all of that with minimal change of heap, and it will actually be able not only to, like cache some data outside of the heap, but, actually build hash tables out of the heap, sort data that is out of the heap, just in the same way as it would treat data inside the heap. And actually, we've done also micro benchmarks, so Flink is as fast in sorting serialized data as actually Java is in serializing, and it's sorting just objects. So sorting data outside the heap in the same speed as objects inside the heap is, I think, something that is sort of unique to this approach that we're implementing there.
One question. In the pipeline execution mode, do you leverage the locality data, or it's completely destroyed?
So yes, so as much as possible the task will be scheduled to where the data is. Yeah. Okay.
So for input tasks, this is a bit similar as it is in Hadoop, right? The split will, or the task that consumes a certain split will have a strong preference to go to the node where the split resides. For any later operators, actually the model in Flink is even a bit different than in MapReduce, that multiple operators, long pipelines, can actually be executed in the same JVM. Also by virtue of this memory management, we can strictly confine operators to certain subportions of the memory so they don't interfere with each other. And then we either stream through a local JVM, or we can say we do strict co-locations from a stream producer to a stream consumer, where that is desired. It is sometimes desired, sometimes it is not, if you want, for some availability guarantees to say, okay, this one is not the same as that.
Okay. Third point, native iterative processing. So this is an example of an iterative algorithm in Flink, probably the most basic iterative algorithm ever. We're trying to find the transitive closure of a graph, so whether a node is reachable by some other node. Yeah. So what we do here is that we're going to get a data set called edges, which is essentially a list of edges. And then we're going to iterate 10 times over this function that is building the next path. So we're building paths of length 2, length 3, length 4, and so on and so forth. We're using union and distinct to not double count the paths. But basically the new thing here is that this iterate operator is a Flink operator. You're not using the loop structure of your programming language. You're not using a for loop or a while loop. You're using a dedicated operator called iterate. The result of this is that Flink will internally build a cyclic data flow with a feedback edge. So it is not going to see your program as a very long list of programs that kind of look alike, but as one program. The nice thing about that, so this has a bunch of performance implications. Another nice thing is that you get a second operator called iterate delta. So here, what you're doing is you're defining two functions, one that is building something called a work set, and one that is building a bunch of deltas. So essentially, you can encapsulate iterations that do not change everything all the time, but make point transformations in some state, and then the system will execute those extremely efficiently. This is, for example, very beneficial if you're doing something like graph analysis. This is the net effect that you get from a graph system like Giraffe. And in fact, there's a graph API in Flink that is largely built on top of this feature. The effect of using these native iterations is essentially that you are going to do only the work that is needed. So in many iterative algorithms, like as I said, graph analysis or machine learning, there is a characteristic that not everything converges at the same speed. So some parts of the model or some parts of the solution need a lot of time to converge, and some of them converge very, very early. If you're using a naive way to do iterations in which you're basically sending the program again and again and again in the system, you're repeating a lot of unnecessary work. Using this native iteration construct, you can actually mirror the actual work that is done. This is from the typical algorithm where after iteration 20, basically very, very little happens. If you were using a naive way to execute that, you would actually be doing the constant work up here. And of course, this has implications in performance. So this is a small experiment of running PageRank on Hadoop MapReduce, Flink using the bulk iterations that do a constant amount of work per iteration, and Flink using the delta iterations that exploit this feature of asymmetry convergence. So this is Hadoop MapReduce for 30 iterations. This is Flink for 60 iterations, and this is Flink delta again for 6 iterations. So what we can see is that in the last 30 iterations, there's actually very, very little work that needs to be done. And here we are doing all this work for no reason. So if your problem or if your algorithm or some kind of library can exploit this feature, this can actually give you a very, very significant boost in performance. This is the case, for example, for Flink's graph library. And finally, the cost-based optimizer. So a lot of these programs kind of look like SQL programs, but are actually not SQL programs, right? So you can get your native language types, and you can create arbitrary user-defined functions. One way is to say that since it's not SQL, we don't know anything about the semantics. We're just going to execute it as is. But actually, even for these programs, you can do quite a bit. You cannot go to the full spectrum of SQL optimization, but you can do quite a bit. And this is an example of that. So these are two execution plans for the previous program. Basically, what we're doing here is we are getting two data sets. We're filtering the first one, and then we're joining with the second one, and then we're doing a group by and sum. And the optimizer will insert these green operators between the functions that you define. These operators, essentially, what they do is the following. So here we're choosing to broadcast one side of the join, and build that as the build side, and build a hash table on that, and forward locally the other side of the join to the hash table, and then hash partition after the join. Here we are choosing a repartition join and basically reusing the partitioning for the end user. So the Flink optimizer will